now we're going to talk about system models. We've looked at the basics of dynamic systems and important system properties. Now we're going to look at system models, and here are some of the different kinds of models we could look at. Schematic diagram, that can be a model of a system. Block diagram is a way of representing a system by showing subcomponents within the overall system. We can have differential, difference, or algebraic equations that describe a system, and that can be considered a model. A state model we're going to look at. Transfer functions. So if you've taken a class in signals and systems, you've seen transfer functions already as a model, possibly block diagrams or schematic diagrams as well. And then matrix fraction description. So we'll briefly talk about each of these in this little section. A schematic diagram basically shows how parts of a system are interconnected. So this is an example of a schematic diagram, and it shows that this is a schematic diagram for a permanent magnet DC motor controlling an inertial load with friction. And in general, the schematic is not particularly useful for analysis or design, but it represents the physical aspects of the system. And so it is a useful model of a system. A block diagram. A block diagram can show how various subsystems are interconnected to form an overall system. And so, in general, also, this is not particularly useful for analysis or design, but it does show us how things fit together in the overall system. We can have differential, difference, or algebraic equations. So these are based on the laws of physics and chemistry, biology, or whatever field our system happens to be in. Again, because we're looking at this from a very general perspective, this can be in many different disciplines, electrical, mechanical, so forth. The equations may be written from the block diagrams or from schematics. So here, for example, we have this permanent magnet motor system, and we can write down the KVL equation. So this is a KVL equation associated with this system. And here is a torque equation for the rotational mass. The rotational inertia times the rotational acceleration is equal to, in this case, these things. So we have these equations. So our system may be represented, instead of this schematic, we may just go ahead and take these equations. And these equations can represent our system. Again, these are not particularly helpful for analysis or design, but obviously they are related to our system, and so if we have a system we're working with, then they are important. It's just it's not helpful, so we would generally want to move it to some other form. A state model is maybe obtained from original differential, difference, algebraic equations. In general, this is a useful model for analysis and design, and in fact, this will be the preferred model for this course. We will be using state models. So a state model is basically has two equations. One is the state equation, and the other is the output equation. The state equation describes how the system is affected, and in this case, the state equation is always a first-order differential equation, a matrix, a first-order differential equation with an algebraic equation. Okay, so this is actually a difference equation. X the next time around is going to be equal to a times x plus b times u at the present time, and so forth. So these are state models, and in general, A, B, C, D are matrices. So this is in continuous time, this is in discrete time. So the state model we'll be looking at And I'll talk a little bit more in this video about state models. Transfer functions may be obtained from, again, the original difference or differential or algebraic equations. They could also be obtained from input-output data. Incidentally, input-output data can also be considered a form of mathematical model of a system. In general, a transfer function, we will consider it to be a matrix of rational functions. When you take a class in signals and systems, usually you assume a system that has a single input and a single output. In general, we will have multiple inputs and multiple outputs. The transfer function is also useful for analysis and design. We won't use it as much as we will the state model, but we will use it a significant amount. I may have a transfer function in continuous time or in discrete time. So we only have a transfer function if we are working with a system that is linear and time invariant. A matrix fraction description is closely related to the transfer function. And in general, it's not directly obtainable from either the equations or data, and it can be useful for design, not so much for analysis. So we can have what's called a right matrix fraction description, where I have an inverse that appears on the right, or I can have a left matrix fraction description, where the inverse portion is on the left. We'll talk a little bit about these. We won't use them very much, but they are useful in some settings. Now let's take a look a little bit more specifically at state models. So given the input at some time n, that is u at n, how much information do we need to know about past inputs, that is u at time k for k less than n, in order to determine the present output y at n? So we can write this way. In general, we will have a state. So x at the next time is equal to some function of x at the present time, u at the present time, and the time. And the output equation is some function, the output y is some function of x, u, and t. This is the general representation for it. So again, the input in general, there may be maybe an m-dimensional vector, the output may be a p-dimensional vector, and the state may be an n-dimensional vector. So in general, we may have that. So in discrete time, we basically have a difference equation where x at the next time is a function of x, u, and t at the present time, and y is a function of x, u, and t at the present time. Y at the present time is a function of x, u, and t at the present time. So the state property says that given the initial state x at time 0 and the input u from t0 to tf, we can compute the output y during this same interval, and also the state in the same interval. In continuous time, we would have them in this form. And now, so instead of having x at the next time, we have the derivative of x is a function of x, u, and t, and y is a function of x, u, and t at the present time. So if the functions f and g are nonlinear functions of x and u, then the system is said to be nonlinear. If it's a function of time as well explicitly, then it is time varying. If it is not explicitly a function of time, then it is time invariant. If it is a linear function of time, linear function of x and u, then it would be linear time varying. So here, the matrix, this is a matrix times x, a matrix times u. If the matrices A and B are actually just constant matrices, then we have a linear time invariant system. And similarly for C and D. So this describes then state models and various forms and how they relate to the system properties we talked about earlier. systems described in this form are causal. Okay, so even though I said the differentiating operator is not causal, notice that this is one way of expressing what's going on. On the other hand, I can rewrite this equation by integrating both sides of this equation, in which case we get x is a function of the integral of x, u, and t, in which case we have the system being causal. We also see that this is associated with a dynamic system, a system with memory. Okay, so regardless of which version we're working with, we have the same thing. So these are system models, an introduction to system models. We'll talk more about system models as we go along.